See, inverting Laplace transforms depends on your knowledge of the actual forms of the Laplace transform. So taking a look at this first one, we want the inverse Laplace transform of 2 over s to the fifth. So the thing you need to do is figure out, well, what gets me to an s to the fifth in the denominator? The denominator is the most important part of any Laplace transform. So after looking through, you probably realize, well, the Laplace transform of t to the fourth is 4 factorial over s to the fifth. So the way I'm going to get to the s to the fifth in the denominator is by transforming some multiple of t to the fourth. So what is that? Well, what we have to do is rewrite 2 over s to the fifth as something with 4 factorial over s to the fifth, so I know to go back to t to the fourth. And since I have the 2 already, I'm going to basically multiply by 2 over 4 factorial. And that is 2 over 24 times 4 factorial over s to the fifth. So that means that the inverse Laplace transform that I'm looking for is 1/12 t to the fourth. 1/12 because of the constant multiple, 4 factorial over s to the fifth goes directly to t to the fourth. So as you can see, we're just basically manipulating constants here. If we look at the second one, the thing to keep in mind here is that the Laplace transform of an exponential function, e to the at, is 1 over s minus a. So whatever you're subtracting in the denominator is whatever you have as a constant multiple in the exponential. So that means here, now since this is 3 over s minus 4, this would be 3e to the 4t. And since there's a 2 in the numerator, that's a 2 multiplied outside, this would be e to the negative 3t. And there is that inverse transform, or should I say the function whose transform is the thing inside braces. Now looking at this third and final one for this video, you notice you have a sum of squares in the denominator, which should tell us it's either a sine or a cosine. Now remember, the Laplace transform of sine of at is a over s squared plus a squared. And the Laplace transform of cosine of at is s over s squared plus a squared. So here it looks like we have a combination of both. And remember, we can break a fraction apart by its numerator. So that means that we have the Laplace inverse of 3s over s squared plus 16 plus 2 over s squared plus 16. Now, 3s over s squared plus 16 is 3 times the quantity s over s squared plus 16. Now, s over s squared plus a number squared is exactly like cosine. So this is going to be 3 cosine of 4t. And if we have 2 over s squared plus 16, well, when I Laplace transform something and get a constant, notice over here it looks like sine, but we're missing something. We're expecting a 4 in the numerator when we have a 16 in the denominator. No fear. I'm going to rewrite this that I have 4 over s squared plus 16, but then I had to multiply by 2 over 4 to get the original 2 over s squared plus 16. So that means that we have transformed 1/2 sine of 4t. So there we have it. So that means that the original function, I'm just going to call it f of t, is 3 cosine 4t plus 1/2 sine of 4t. And there we have some basic inverses. Next video, we'll talk partial fractions. Thanks for watching.